Good afternoon to everybody. Welcome to this session where we have Spotify sharing with us how they use Google Cloud Platform in their backend infrastructure. We have Nelson Arape, a software engineer from Spotify here, so this talk will be in English. I am Giovanni Galloro. I am a customer engineer in Google Cloud Italian team. Here's the agenda. We will start with Nelson doing an overview on Spotify and on their event delivery system. Then I will provide an overview of Google Cloud Platform and its most important feature. Then Nelson will go through the description of the architecture of the various components of their event delivery system, and I will help him in describing the Google services that are involved.
Hello. It's a pleasure for me to be here. So, before jumping in our system, I would like to do an introduction of what is Spotify. I hope some of you know what is Spotify already. Yeah? Okay, most of you. Yeah, we are a music streaming system, and at the beginning, our key feature was this huge catalog, and the feeling that all this catalog is on your device. So streaming this music really fast was one of our key features. And yeah, it was great, but now it became a commodity. So people, yeah, this is the expectation. How else it could be? So to be on top of the game, we need to leverage the data that we have collected about our users. And so we are collecting this data, creating new features, and making available to our users. If you are a user of Spotify, this is something we released a few weeks back, is that we show you what you have been listening in the previous summer, so you can remember, yeah, this was a catchy song that I was playing at that time. Also, this is delivered based on data. We create a personalized playlist for each user. Also, Discovery Weekly. We present a playlist of songs that we think you will like, but you have not been listening to. So this is a great way to discover new music. So all this happens is because we have the data being generated on the clients, go to our event delivery system, and then from there we do several stuff, like building these recommendation engines. Also, very important, we need to pay our creators, the music creators, labels, artists, and songwriters. So we do A/B testing to understand how our users use our products, and so on and so on. So I will say our event delivery is in the start of this journey. So basically what we do is we collect all this data and make it available in a distributed storage, so our downstream user could build data pipelines that will take this data and do crunching and investing in these new features. Something that I have to say, we are 140 million monthly active users. We are consuming 1.5 million of events per second. This is about 60 terabytes of data.
Okay, so let's provide an introduction about Google Cloud Platform. As you probably heard this morning, Google has some or many probably products that are actually used by more than 1 billion of users. And anybody of us has the visibility of the level of scalability, of performance, and availability of these products. What Google want to do with Google Cloud Platforms is to let their enterprise customers use the same platform, the same technology services, the same hardware, network, software stack that you heard about this morning, that Google itself used to run his products. Google wants to let this platform be available to their enterprise customers so they can run their products on this platform. During the years, Google developed a series of technologies to run its products, technologies that became technical papers, white papers, starting from Google File System, and then to MapReduce in 2004, that then became the Hadoop open source project, and Dremel and Borg, for example, that became Kubernetes or TensorFlow. And in Google Cloud Platform, you find the same technologies, productized as a service for customer that you see here, divided in compute services, database services, storage services, machine learning, and big data. One thing that in Google Cloud Platform is always has been trying to do at the maximum extent is to provide serverless components, is to provide components where users has only to bring their code and their data, or then their code or their data. And all the infrastructure provisioning and management is done by Google, by the automation that's in the platform. This started in 2008 with App Engine. It's the platform as a service where who deploys application can deploy application directly on the platform with development tools or code deployment tools, and then continued with the services like Cloud Storage, BigQuery, and Cloud PubSub that are used by Spotify too, and that will be discussed in this session. But we know also that in some transitional period in cloud adoption, and to address some specific needs related to specific customization, the traditional virtual machines, infrastructure as a service, sometimes are the best option. So this will be part of this discussion too, and this is an area where Google is continuing to innovate.
Thank you, Giovanni. So I will give first a design overview. This is our platform in very high level. We collect events from the clients, and we produce those events into PubSub. This helps us to collect data from all our data centers. We still have on-prem data centers and also Google ones. But anyhow, we collect all this data around the world. We use the amazing Google network, and then we pull that data from our consumers and then make it available in Google Cloud Storage as a set of files. We have a specific format that we will talk about this later. And yes, because we want this event delivery system to be a self-service, we have an automation deployment that our developers just configure what events they want to send, and we are able to deploy the infrastructure using Google Cloud API. So we don't have to be blocking anybody. They just configure and are able to deliver.
Thank you. In the design that Nelson showed, there are 3 hexagons, 3 Google Cloud Platform components. One of these is PubSub. PubSub is a messaging service that completely managed messaging service that provide asynchronous messaging between independent applications. It basically implements publisher-subscriber architecture where there is a publishing application submitting a message into a topic and a subscribing application that has subscribed to a topic of interest and retrieve the message when it comes online. PubSub can act as a buffer between applications because his message store can hold the messages until the subscribing application is ready to receive the message. And it has dedicated capacity in all Google Cloud Platform region. It has been tested to have sub-second timing in notification and in message delivery, even when has been tested at 1 million events per second. And it uses HTTP, so the publishing application could be any application supporting HTTP GET request. Subscribing application can act in two ways. In a pull way, it has to support HTTP GET request, and in a push mode, where PubSub push messages directly to the application, the subscribing application has to expose a webhook supporting HTTP post request. Another component is Google Cloud Storage, is an object storage where data are stored and are served as binary objects. It supports an unlimited number of binary objects with a maximum size of 5 terabytes. And it can be used, for example, to serve web content because it's accessible with HTTP protocol, with standard web protocol. It can be used to host and to store data related to archival or disaster recovery, or to provide to users access to download access to big files. Google uses this service, this Google Cloud Storage, as a backend storage for media files in Google Photos, for attachment in Gmail, and for all the documents in Drive. It provides replication and high availability, so customer doesn't have to manage high availability. It is accessible, as I said, with HTTP, with XML API, JSON API, and with the Google Cloud Platform console itself, or GSUtil command line. It provides different storage classes, these different SLA, multi-regional and regional are for data accessed very frequently. In multi-regional, you have data replicated between two regions in the same macro area, for example, in Europe, in US, or in Asia. In regional, you have data replicated only inside one region. Nearline is for data that is accessed less than one time a month, and code line is for data archival storage, mainly for data that is accessed less than once a year. Then we have BigQuery. BigQuery is basically a completely managed service that provides the users the ability to perform queries, analytics, reports on a huge data set with a very fast performance. It's our equivalent of an enterprise data warehouse, with the difference that users have only to load data and perform the queries. Users doesn't have to allocate capacity, provision server. User doesn't have the notion of capacity neither, because capacity is allocated dynamically on demand when user perform the query based on the amount of data on which the query are performed. And it support access via JDBC, ODBC, via BigQuery API, command line, and HTTP UI. and then back to the Spotify architecture.
Thank you. So, the first diagram was very high level. This is a level deeper. This is still the three big areas, so we will start with the producing side. So, as I told you before, we produce more than 1.5 million of events per second. This is like average because there is a daily pattern. We have high tide and low tide. So, and this is how it looks. We have our clients send events. They eventually will reach a microservice in our data centers. So each of these microservices will write the event as a log line, as a sys log line, as a text. So on those hosts, we have deployed a daemon. We call it the file tailer, because what it does is just that. We tell the log line and make sure that that event has been pushed successfully to our event delivery system. It reads line by line, if very dumb, doesn't have much logic. Send it to our next component, the event service, and then if it gets 200, it says yes, it was persisted successfully. It also, this log line could be like a stat trace, so it will receive an invalid code. So okay, I don't need to retry, but if it's not at 200, this is not an invalid code, so he will retry to make sure the data have been pushed and we don't lose any data. This is where the business logic is happening. Here we parse the text line. We have a schema definition, so we'll make sure that this match one of our events. We also convert it to Avro because we will push Avro binary from this point until the end. We also check this event against a whitelist because it's easier for us to do a changing in this whitelist to prevent publishing some event than rolling out a change to our clients to stop producing that event. So spending is good, but waste is not. That is our motto in Spotify. So if we don't need to send that event, we will just say, no, invalid, don't retry it. So if everything is okay, then we push this event to Google PubSub. And we use one topic per event type. So this provides very good isolation. We have not all the events are the same. And we have metrics related to the specific event type. So we like it this way. Then, on the consumer side, we have all those events arriving in PubSub topics, and we create subscriptions, and then we pull that data using ETL processes. I will explain further how this ETL looks like, but then once it pulls that data, we do some touching to that data, for example, removing duplicates. Our clients resend events, and also being a distributed architecture could have duplicates all the way. So this is the component that handle that, and then make it available in Google Cloud Storage. And we use a very specific format. This is how it looks. We use Cloud Storage has something called buckets. Let's say like a drive, a place where I can store objects or files. But inside this bucket, we have a semantic bucket of event, date and time. So we say, okay, this specific date, this specific hour. We will store in that folder all the data have been happening for this specific event. So once we think we are consuming all the data, we say, okay, we mark this hour as complete. So this is how it looks in time. Yeah, we are making this data as a complete, because until that point is when our downstream user will start to run and consume this data. We don't want to say, okay, downstream dependencies, please start your crunching time, and then later modify that data set, because then we will need to retrigger our dependencies, downstream dependencies, and then they will need to retrigger their dependencies too. So we take care of not doing that. We treat, once we mark a folder as complete, we don't allow to modify that data. But because everything could happen, let's say we have an hour that we already marked as complete, but suddenly late data arrived for that hour. This could happen because we use heuristic to determine when it's time to close the hour. So the heuristic is not always 100% fine every time. So what we do is that, yeah, this is already closed, but then we will move these few events that arrive late to the next hour that is still open. So our downstream users are aware of this, so they will know that if, for example, this hour 3 potentially could contain events from hour 2, for example. So
So in this consumer side, Nelson will introduce other components that are part of Google Cloud Platform. One of these components is Cloud SQL. Cloud SQL is basically a completely managed database as a service offering that provide application-level access to MySQL DB or PostgreSDB. Users have to configure only the compute capacity needed, the storage capacity needed if they want replication, and the Google Cloud Platform automation manage operating system, patching, backups, and replication between zones. It exposes a basic connection string that you can use, the user can use in their application. Another component that is used in the consumer part of the Spotify event delivery system is Cloud Dataproc. Cloud Dataproc is a managed service, again, that provide Hadoop and Spark jobs. Hadoop and Spark cluster. It automates the deployment of the cluster, the management of the cluster, and Spark and Hadoop jobs always require a large amount of data, a large number of nodes. So in this case, the elasticity and scalability of cloud can help because, for example, you can pay the resource only when you have a job to run, and then you can shut down the nodes after the job has run. You can have the resources immediately available, and you don't have to wait for a server to be acquired, cabled, installed, and software to be being configured. And you can scale at the maximum extent, number of nodes. So the fact that you are not allocating capacity, but you are using capacity only when you need to run the job, enables you to run it at the maximum number of nodes and finish the job sooner and having the business result quicker. And then let's go to the rest of the architecture.
Yeah, okay. So this is a zooming of what our ETL looks like. We decided to build our ETL as 3 microservices: consumer, completionist, and deduper. So the consumers is a very dumb process. He pulls data from PubSub, and then it will write that data as, it pulled a batch of events, and will write this batch as a small file in the one intermediate Google Cloud Storage. So we put it there, and then we notify this other component called completionist. I will explain more what it does. And when the completionist say, okay, yes, I I persist your notification that you have a new file with data, then it's when the consumer acknowledge pops up. This, yes, I have consumed successfully this batch of events. If something happened in this, and for some reason we are not able, or the completionist didn't return, or we have some problem writing to Google Cloud Storage, we know that because we didn't acknowledge those events are still safe, stored in the PubSub. So by doing this, we are making sure that we are safely moving the data from PubSub and make it available as files in Google Cloud, this intermediate bucket in Google Cloud Storage. So this completion is the name is because this is the component that decides when an hour is complete. So for doing that, it uses Cloud SQL as a database. So when it receives a notification, yeah, the consumer has produced this file for this event at this date and hour, so it will store that in a database. And this is where the heuristic of completing the hour is stored. So here we use when was the last time that consumer wrote a file, how the backlog in the Google PubSub looks like. We are able to get a metric that says what is the timestamp of the oldest event that haven't been acknowledged yet. So there we know, yes, we still have data on Google Cloud Storage, so we cannot close this hour at this moment. So once all these conditions are met, just the completion is that decide to close an hour. And then if the, for example, in the producer side, this is what could happen. Suddenly, we emit events, a few events for all the hours, so consumer will put it, and then the completion will say, okay, no, sorry, we already closed this hour, I will move it to the next. Then the last component is the duper. The name is because here when we do the duplication. This is a MapReduce job that runs on Dataproc. We have a scheduled service, it's open source, called Sticks, that when it's time to run, we say, please run the duplication job every hour. So when it's time to run, it will trigger this job. Then the duper first asks the completionist, is this hour complete? If it is, it will return a list of files from the intermediate storage. So this is a list of files I need to read and duplicate. So after this initialization, the duper job is just a MapReduce that runs out the duplication. This is written in Apache Crunch. And we spawn a Dataproc cluster just to run that job, and when it finishes, we tear down that Dataproc cluster. And yeah, we make it available on Google Cloud Storage. So I have explained how we produce, how we consume. Now the missing part is how this gets configured. As I told you before, we don't want to be a team that blocks other developers on Spotify. So we need to manage these 250 event types, and these present two challenges. One is that, yes, it's a lot of event types that we need to make it in a way that it be configurable. And the other is that event types are not the same. We have, for example, one event type is every time a user has played a song. But we have other event types, for example, a feature we are developing that only few beta testers are using that feature. So we go from hundreds of events per second to only a few events per minute. So we need a way to scale the consumption to know, yes, for this event type, we need to pull a lot, but for this other set, with only few per minute is enough.
So to address this scale needs, what are the services and the capabilities that are in Google Cloud Platform? You can scale instances in a vertical way, so you can add more capacity to a single instance. You can do that on Google Cloud Platform with the advantage that you have custom VM types, so you can provide to an instance exactly the amount of CPU core and the amount of RAM that you need, no less, no more. You don't have to be bound to fixed VM sizes where there is a predefined ratio between number of core and gigabyte of RAM, and this is very helpful. And during the usage, your resource usage is monitored, and you get from Google Cloud Platform console suggestion. For example, if you are not currently using efficiently all your capacity, you have suggestion to downsize your instance, and you have estimate of the billing saving that you can do. As on the other side, if you are reaching the peak of the capacity you provided, you have suggestion to increase the capacity assigned to your VMs. But vertical scalability is often not enough, for example, because you reach a limit and you are unable to scale to provide, to serve all this number of users, this number of events. So if you want to overcome this limit, you have to use horizontal scaling. You have to add instances to multiply the resources assigned to your service. You do this in Google Cloud Platform with Managed Instance Group, where a set of instances is managed as a single entity. They are completely equal among them, so their configuration is based on an instance template where you decide what is the base image on which the instances have to be based on, what is the configuration, what is the network configuration, the startup script, etc. And then you deploy these instances. You can have regional managed instance group, where you deploy the instances across different zones in the same region, and you have a load balancer spreading traffic between them. So you have fault tolerance, you have high availability if one or more instance or a complete zone goes down. And you have auto-scale too. So you can configure auto-scaling, so instances can be added to your managed instance group if your load increase, and can be removed if your load decrease. And you can do that based on different metrics, for example, CPU usage, or number of requests hitting your service, or a custom metric too. You can do rolling upgrade if you need to upgrade your code. You can update your instance template and trigger a controlled update that will update your service in a progressive way, not disrupting your services. Your user continue to work. And you can configure auto-healing, so when your instance doesn't respond to an health check that you configured, your instance will be killed and will be replaced.
Okay, so going back to deployment automation. So we have our which events are defined in the system, we have a distributed config service, and we use this first on the event service to populate the whitelist, so we are able to reject those who are not in this whitelist. And we have a deployment service that talks to Google Cloud Engine, and then every ETL is a managed group, GCP managed group, with an autoscaler policy of CPU usage. So our consumer, this is the one we treat this way, is very simple because we don't need to handle how big or how small is the event. We just say, okay, we are pulling, and the more backlog is in Google pops up, the more CPU users will consume this consumer, and then autoscale policy will decide, oh, looks like we need more VMs because the threshold is higher than the one that we set. So we have autoscaler deploying more VMs, so we are pulling more data from PubSub, but across many VMs. And we decide to use all small VMs, so we don't waste too much resources on those few events that are only a few events per minute. So we have a small VM, but we have with the autoscaler to, yes, for those that we need more resources, please spawn more machines or more VMs.
Okay.
Yeah.
I think we are done. I don't know if there is time for questions or... We have 4 minutes, right? If there are questions.
Yeah. Anyways, we will be outside here if you want to approach personally.
No question, probably. Oh, a question.
Hi. Why are you processing the message before pushing them to PubSub? And why not processing them after after retrieving them from PubSub?
You say why we don't push from clients to PubSub?
Yeah, something, or I mean a dumb interface between the two, because here you're doing applying some logic that could be time consuming.
Yeah, there are two answers for that. One is legacy. The straight answer is that before we use a system based on Kafka, and I can talk about some scars that I have because of that system. So we decide to build the system keeping the same API in the beginning and at the end. Right now we are working on a library to publish directly from here from here. We still want to dev service, we want still some controls. We don't want to push credentials to all our microservices, but we will skip these 2 steps and publish directly.
Okay.
Okay? Thank you.
We are done. Thank you.